Hey, math people, big moment. Welcome to Multivariable Calculus, Calculus 3. Wow, okay, so this course really opens up your eyes. We have been constricted. Our whole lives we've been constricted. Your whole math journey life. I think of whole life as like, what you learn in math class, right? You've been constricted to, and I'm getting the lesson ready right here off to the side. Here it is. You've been constricted to the plane, man. Think about this constriction. Think about the freedoms we have in life. We can jump. We can fly in metal objects. We have depth in a few different directions. 1, 2, 3, 4, 5, 6. Those aren't 6 directions. Up, down, left, right, forward, center. Those are 3 different dimensions. Live in 3D space. 6 different directions, but up and down the same, left, right the same, forward, backward the same. On the plane, we don't have access to that, right? The way you see me right now in this video, I'm 2-dimensional, right? But I swear in real life, I occupy space. Thing is, this is restrictive to stay on just the plane. How about we lift ourselves up, people? Like how motivating this is, and observe space. All right, so we're applying calculus to surfaces now in space, not just the mere line y is equal to x, but instead in space, like I said. So that's the objective today, is just to build our understanding of 3-dimensional space. All right, so can we do that here together, people, before we start applying multivariable calculus to it? So the study of change in functions that are expressed as more than just single variable equations. All right, so let's draw some parallels between R2 and R3 and see what some of these things look like. Plot some points, draw a sphere, look at a ball, and then just end the day. All right, so just a light intro to what's to come here. All right, so remember, this video is for you, Paul. Did I use Paul already? Whatever. This video is for you, Paul. So skip around and use the timestamps, pause, watch what you need. All right, let's do it. So the coordinate system, where we were once used to the plane, now we are entering space. So those are the difference, right, between the two. Plane, space, plane, space. And we once graphed ordered pairs on the plane. We're now graphing ordered triplets in space. 9, 8. Right, ordered pair on a plane. 9, 8, 7. Where are you? There you are. Ordered pair, or ordered triplet in space. What it looks like. Okay, so we're used to looking in R2, we're looking at the XY plane. Now we're looking at 3 axes, right? They all meet at still the origin. That's still the origin, 0, 0, 0 now. And it's just a addition of a z axis. So if we were looking on like a whiteboard, the XY plane, I generally like to take my marker and then I stick it right here, and I say, whoa, entering space. So yeah, we're used to just having 4 quadrants. We now have 8 octants, right? So you can occupy, so 1, 2, 3, 4, but then you have below the XY plane. So 4 times 2 above below is 8. Okay, what do we graph? We're used to graphing in R2 curves and lines. Curves, bottom line, curves. And then we can still graph curves in space. They're called space curves. But we're now also graphing surfaces. So a curve in space, space curve, just throw in an adjective. But now if you were to graph f of xy instead of just f of x, you would get a surface. Oh, and then, just like the line being kind of the baseline graph that you would start with in terms of your first curve. Your first surface we're going to graph is the plane. So we're going to start there. Some key features of each. So we're used to saying y-intercept, x-intercept when you cross through the y and x-axis respectively. You can still do that. You can still have a y-intercept. You can still have an x-intercept. You can now have a z-intercept. But you can also intercept through planes now. So we would call the plane that shares the x and z axis as the xz plane. So I like to, and everyone does, like to think about this as like a corner, corner of a wall. So where your two walls and then the floor meets. That corner where the floor and the two walls meet is this origin point. And then one of your walls is the xz plane. The other wall is the yz plane. And then the ground would be the xy plane. So we're treating, and that's just by convention, but we're treating that as like that z is equal to 0 is kind of, we were graphing, right? When z is equal to 0, we were graphing on the plane all along, right? That's kind of the idea of how we're observing this. So like this 9, 8 would be, 9, 8, 0, right here. These are the same. Okay. Distance formula. All right, 3, 2, 1. The distance formula in R2 is just your square root of your change of x plus your change of y. This was just like a fancy Pythagorean theorem. So it's like c squared is equal to a squared plus b squared. Well, you're adding an extra component. So you're adding an extra dimension, so you're adding an extra component. So you just have plus that change in z squared as well. You're just tacking that in on side of that radical. And then I kind of alluded to this already. So the function notation, we're used to y is equal to f of x. So we're going to cover functions of several variables a little later. But for now, we're just kind of highlighting it. Y is equal to f of x creates that curve on the plane. And then z is equal to f of xy. That creates a surface in space. Okay, so yeah, we're just going to compare, like, what if I were to graph this on the plane and then graph this in space? Like, how would that, and we're going to use this Desmos tool to view it. How would that change? On the plane, we know what this looks like, but what does it look like in space? So I'm going to highlight that right now, 3, 2, 1. Use Desmos 3D. Look, so I'm going to go ahead and just graph it on the app here, Desmos 3D. If I were to graph x is equal to 1, on the plane, so bird's eye view here is what I like to say. It looks like this. I guess we'll do it in pink as well, or red, whatever. So this is what it looks like on the plane, and I can go back to this, just like the literal. Oh, I'm getting too happy here. I'm getting antsy and prepared to write z a lot more. I'm super pumped. But anyway, we can go back to the plane and we can just go ahead and graph that. You can see it's a vertical line. It's just a vertical line. But when we extend it into space, we end up getting a plane, right? So just trying to match it with this. Whoa. Yeah, you can have lots of fun with it on Desmos. You get all these different views, which is nice to see. I think there's another cool feature. Where is it? Oh, it's this. It gives you like a different depth, field of depth. All right, looking at the next one. If I were to graph y is equal to 2x plus 3. Oops. So on the plane, it's just a line, right? Mx plus b, good stuff. But extended into space, looks like that. So yeah, it's still just a vertical, just like a perfectly up-down plane. You can see it in different angles. But this time around, I don't like how I made it look like it had a slope here. It does not, because the bird's eye view is just that line. Yeah. So how would you create something that has like a bit of a down slope rather than just like a wall? Right? That's what I want to highlight during this little segment here a bit. All right, go ahead. If you want to try to guess what these might look like, feel free. But we're going to look at these in R2 and R3, 3, 2, 1. Just doing a few at the same time. So let's go ahead and look at the first case here. If I were to graph x squared plus y squared and set that equal to 25 on the plane, right? On the plane, we would just get this circle. It's just an equation of a circle of radius 5, right? So there's your radius. But if we, again, extend this into space, notice how none of these expressions had a z. That means that this function doesn't depend on z. So z can be whatever it wants to be. So it's just this for any z value, because z has no impact on this equation. So that's how we get what are called cylinders. This is specifically a circular cylinder. There are different types of cylinders in this course we'll get to later. But that's what we're looking at for the first one. If we're looking at the second case, this may look familiar, this x minus 1 squared over 2 plus your y minus, I guess, plus 2 squared over 4. Maybe you might, and it's kind of cool to see these graph in real time as I'm just typing in expressions. Maybe you might remember this as the ellipse back in pre-calc. It still is an ellipse, but again, since z is not present within this equation, we extend, z could be whatever it wants to be, extend all those into space, and you end up getting an elliptic cylinder is what we call that. Okay, now let's start graphing like stuff with z. So if you were to graph z is equal to 4 on the plane, notice how it never touches the plane. If I were to go over here and graph z is equal to 4, now, of course, it's going to be like, what do you mean by z? Right? But what that is between my nose and this xy plane would be that sheet that is z equal to 4, and that's just kind of hovering above the xy plane. Right? Actually, I can just make this a general constant, and you can see here I can just kind of bring this up and kind of bring this down. So, you know, here's my ground floor, and then above and below it. So yeah, this is just strictly not visible at all on the xy plane. And R2, not visible. This would be like, well, I like to have fun with the course, and I like to say, like, what would this look like? We live in R3, you know, like spatially. So if we had like a 4-dimensional sheet of, I don't even know what that would look like, a 4-dimensional object that's like not on our in our space, we wouldn't be able to see it. So it's fun to extrapolate this course into higher dimensions. Because that's kind of the point in some ways. All right, then looking at the last case, if I were to graph z is equal to 2x minus 3y, z is equal to 2x minus 3y. Of course, it's going to graph the plane right away, and that's how we get that kind of like sloped angle. We create it as you know, a coefficient of x, y, and z. You know, z has a coefficient of 1 here technically. But, you know, what would this look like on the plane? Well, z is equal to 0 on the plane. Like, we live in, like, a w is equal to 0. Like, a fourth variable is equal to 0 because we live in a space. So a fourth variable would be 0. So in space, if that third variable were to be graphed on the plane, z is equal to 0, it's just 0 replaced in for z, 2x minus 3y. And it would just look like this. Right, so I can even do it this way. I can set z equal to just 0, which is like just on the plane, and this is what we're looking at here. There it is. Yeah, same thing. All right, but obviously, if you get rid of that restriction, the whole point of this class, you can see that we're now in space. All right, give the next round a go. Give it a go. 3, 2, 1. When I say give it a go, I don't know. Like, envision what some of these things could look like. All right, so done looking at that. I'm getting a little dizzy. Actually, I'm not done looking at it. Getting those different depth angles there. All right, so looking at the first, I'm just going to write it this way. I'm going to write this as z is equal to x squared. Ooh, and I also want to, so this is what z is equal to x squared looks like. We would call this a parabolic cylinder. It's just a parabola, but just cylindrically forever because y is not present within my equation. So y can be whatever it wants to be, right? If I were to fix y to be equal to 0, this is just like a little side note. You know, you could say on the x z plane, it's a parabola, but you know, if you allow all three variables, so you allow a y-axis, it would extend into space like this. But anyway, looking at these down here. Okay, so yeah, if I were to graph z is equal to x squared plus y squared. Okay, so we were just looking at a parabolic cylinder. This is a paraboloid. Okay, yeah, so think about it, right? You kind of get this like circle-y effect. X squared plus y squared should look familiar. X squared plus y squared is equal to 1, is equal to 4, is equal to 9, is equal to 16. These are all circles of radius 1, 2, 3, 4, respectively. So yeah, these are just circles. So if you were to take like z is equal to 1, z is equal to 2, z is equal to 3, and just take these like, you know, perfectly perpendicular to xy plane slices. Think about like Fruit Ninja or something like that. You get that perfect cut. You know, all these cuts would be perfect circles, right? Those are a perfect circle each time. Circle, circle, circle. Anyway, so we get a paraboloid here, parabola-ish, right? Oh, but this is where it gets kind of curious. What would this look like on the plane? Well, we would just say, well, z is equal to 0 on the plane. Or actually, I wonder if it would be happy with that. Z is equal to 0. And it doesn't really like it, but technically, here's my technical. It's like, it looks like nothing. Technically, it's a point on the origin because the point 0, 0, 0 just works. It satisfies this equation. So it would just look like, it just exists for just that little moment, just right there. You know, there's an over-exaggeration of what it really looks like, right? A point, by the way, we can't actually, a point has no depth. It has no dimension. So like, you know, this is what it would really look like. But technically, there's a point there. All right, so the next one, we know that x squared plus y squared equaling a number is some circle. So what if we add a z squared, x squared plus y squared? Oops. Plus z squared equal to 1. We end up getting a sphere. And, you know, I can play around with this a little bit. If I create a slider for r, right? Ooh. It's interpreting it as polar coordinates. I don't like that. I'll just do like a k. There we go. We can kind of increase the size of the sphere, right? All right. Well, we get a sphere. So circle is just x squared plus y squared is equal to 1 on the plane. Projected into space, or extended into space, it creates that cylinder, as we kind of covered over here. And if you add that z squared, you get the sphere. All right, for the next one, you get an ellipse. If you just graph this on the plane, it's going to take me a hot minute to type out, but it's what it is. If you type this and graph it on the plane, you could just think, okay, well, our z component is just 0. So I can just like plug in 0 for z. I'll even do that just to kind of show you what that looks like. I'll plug in 0 for z. So if z was exactly 0, it's just the ellipse, which is just going to be what's called, you know, the three-dimensional version is going to be called the ellipsoid. It's going to just be the where the ellipsoid crosses through the xy plane when z is equal to 0. Bam! Here's the, it's looking like an M&M. Maybe I'm just getting hungry and it's lunchtime right now. Here it is. Yeah, you get an ellipsoid. You get like an egg shape. I actually kind of liked white, or looks like an egg. You get this egg shape for an ellipsoid. A lot of these you don't need to know big time right now. This is just me like exploring with you. You don't need to know pretty much any of these. There's a section that I'll do a little later on. I think it's like lecture 6, where I'll cover these a little bit more in detail. You gotta get your feet wet though first and build that new vision into multidimensional space. All right, but specifically the space we're in together, R3, the space of 3 dimensions. Okay, next one's cone. So yeah, if we were to graph, same logic for the paraboloid, it would just look like a point on the xy plane. It's a squared plus b squared is equal to c squared. It's just, you can see there's a, you know, kind of like a right triangle kind of happening right here, right? Any way I spin it. So you get a cone from this one from squaring it. If you get rid of that square, you get the paraboloid. I don't know, you get just lots of cool, fun, different shapes. I mean, you can do wacky things with this. All right, that's all I really, I want to just do a fun graph. Because you can do lots of cool stuff. Let's create some water. So, there it is. Whoa, wait, that's not how water behaves. This is how water behaves. Point is, you can do a lot with this little, like, there it is. You can do a lot now, all of a sudden, because we've opened up access to another dimension. Whoa. Watch out. All right, so yeah, let's go ahead and plot points in space. Use your intuition. If you were to plot 1, 2, 3, well, where would that land if we were to graph it here? And then, so I use this new word, find the projection onto the xy plane, yz plane, and xz plane. All right, well, the point is what you would expect it to look like. So, you know, let's go ahead and skip on to this. 1, 2, 3. It's projections onto the xy plane. So you can either extend into space or project onto a plane. Would just be, you plug in 0 for, like, where would where would its shadow exist? If I were to flash a flashlight, yeah, onto this coming from the side that I'm currently kind of viewing it at, me looking at the screen, the shadow would project itself onto the xz plane. So that would be when y is equal to 0. So the shadow would, assuming I'm like directly behind it, I guess, would be at 1, 0, 3. That's the point on the xz plane when y is equal to 0. The point on the wall. I flash the flashlight, and this is where the shadow would be on the wall. All right, you do that same process for each of them, right? So more or less on the xy plane, z is 0. On the xz plane, y is 0, and on the yz plane, x is 0. So you can kind of see here, here, and here. All right, distance formula. So we already covered it previously, so to give it a go. 3, 2, 1. So we're just applying it in a way you would expect, which is just finding the difference of the x's, difference of the y's, difference of the z's now, and then squaring each of those values, taking the square root of sum of squares, which you're going to hear me say a lot in this course, square root of sum of squares. And you end up getting root 155. So distance formula behaves the same. Right, so just maybe what did we just do right there? What does that number represent? It represents the number of units in between, whatever your x, y, and z axis units represent. It could be meters, could be feet, could be miles, whatever. Right, it's the distance between these two points. Could be astronomical units, whatever it is, because we are now in space. All right, so last one here, show that this is a sphere. Okay. Find its radius and center. All right. My hint is complete the square. 3, 2, 1. All right. If you remember completing the square, what you can do is you can clump your x stuff, clump your y stuff, clump your z stuff, and then complete each square. What that would enable is it would enable you to write it in this like x minus h squared plus y minus k squared plus z minus l squared is equal to r squared format. This is the equation of a sphere. Where h, k, and l together as an ordered triplet represent the center of the sphere. And I can even show that. We got a little time. I like to make these less than 25 minutes. So we have x minus h plus y minus k plus z minus l. And that's equal to your radius squared, which we'll just use as like b right now because r it'll get confused on. Oh, I didn't square any of these. Yeah, it's a plane if none of those are squared. All right, so here we go. So h moves it like, what would that be? Parallel to the xz plane, moves it in that direction. K moves it parallel to the yz plane. Here we are. And then L moves it kind of up and down. So that would be, I guess it would be a better, you know what, I like this language a little bit more. This would be perpendicular to the xy plane. This would be perpendicular to the xz plane, and this would be perpendicular to the yz plane. There it is. Better way of wording it. And then B just represents your radius. Okay, so anyway, what I did was I clumped all the x stuff and then I completed the square. I took 4, I cut it in half and squared it. That enabled me to write this expression in a way where I can easily extract out the center and radius. I did the same thing for y and for z. Here's what this equation looks like when you complete the square 3 times over. Move your constants onto the right side, and you get a radius of 3 and a center of -2, 3, -1. So this is how I'll end the day here. People. So I'm gonna get rid of all these sliders. What I'll do is I'll write this out. This is gonna be a +2. This is gonna be a y -3. This is gonna be a z +1. And this is equal to 9, which is 3 squared. Here it is. And then if I were to go ahead and make this translucent, I can plot the center at -2, -3, -1. And you can see the center right there. Okay. That's it. Welcome to space, Math On.